when a photographer with a 300mm lens meets a photographer with a 400mm lens. The photographer with a 300mm lens is defeated. Or maybe not. Welcome to Virtual Pathfinder channel. This video is about the comparison between two telephoto lenses for astrophotography. The lenses are two Tokina mirror lenses with focal lengths 300mm and 400mm. The lenses are tested on a Micro Four Thirds camera, which has a crop factor 2 compared to a full-frame camera. That means that the lenses have a magnification corresponding to a 600mm and an 800mm lens on a full-frame camera. Before we start, I would like to remind you to subscribe to this channel, and if you want to support the channel so that I can make more content available, consider supporting the channel on Patreon. There are exclusive material available there. There is also Virtual Pathfinder merchandise available on Pinterest. Now let's get started. Here are the contents of this video. First, I will talk a bit about Tokina mirror lenses, then mirror lenses in general, then a word about optical resolution, and then we can move on to the comparison of specification for the two lenses. I will make an image comparison of the moon and a deep sky object. Finally, I will end with some conclusions about this comparison. First, a few words about the company, and the pronunciation in Japanese is Tokina. So I used to say Tokina, but anyway. Tokina is a Japanese brand which has a history dating back to the 1950s, and it's owned by the parent company Kenko. Tokina is known for making optical designs such as teleconverters, optical filters and lenses. I have used a 300mm mirror lens from Tokina for some time, and it's specifically designed for the Micro Four Thirds system. Apart from its excellent optical performance, it's surprisingly small and lightweight. Recently, I purchased a Tokina 400mm lens, which is a bit different. Apart from being slightly bigger and heavier, it is not specifically designed for the Micro Four Thirds system. It has an adapter ring at the back end closest to the camera, which can be replaced to fit the lens to other standards. That creates possibilities at the same time as it can be a drawback. I will get back to that later in the video. The reason I was interested in the 400mm lens was because I had a good impression of the 300mm lens, and the longer focal length in combination with the wider aperture would make it closer to a compact telescope. I have made a comparison of the two lenses regarding astrophotography, in this case details on the moon and one deep sky object, M42, the Orion Nebula. Before we get into that, let's have a look at the characteristics of mirror lenses in general. Mirror lenses are catadioptric optical systems, just as telescopes like Maksutov-Cassegrain telescopes. The optical design is a combination of lenses and mirrors. As you can see in the image, the light from the observed object enters the lens from the left through a glass lens. After passing through the glass lens, the light is reflected by a primary mirror at the back end of the lens barrel. The light is then reflected by a secondary mirror attached to the front lens. Finally, the light then is refracted by lenses when the reflected light exits the back end of the lens. The light is focused at the image plane, which is on the camera image sensor. This is a very clever design which has some advantages. It becomes very compact since the optical path is folded twice by the mirrors, so that the light is passing 3 times the length of the lens. Small size also reduces the weight. This is in line with the philosophy of the Micro Four Thirds system. Another advantage with mirrors is that they don't introduce chromatic aberration, which is more common in refracting lenses. Mirror lenses usually have no visible purple fringing. So far, it seems mirror lenses seems like a good deal. But unfortunately, there are some downsides with this design. The secondary mirror creates an obstruction of the incoming light, which causes some problems with the resulting image. The image tends to have lower contrast compared to ordinary glass lenses. The colors appear slightly washed out. This can be improved in post-processing, but the images straight out of the camera tend to look a bit washed out and mediocre. With some work, they can be really good. Another problem with mirror lenses is that they have very shallow depth of field and are a bit hard to focus. The shallow depth of field is not a problem for astrophotographers since the focus is fixed at infinity, but it is hard to find the best focus using the focus ring. The lower contrast can make it even more difficult. Still, with a well-designed mirror lens, it can be sharp. The two lenses in this comparison are completely manual with fixed aperture. That is typical. As a side note, the only autofocus mirror lens I've heard of was made by Minolta a long time ago. That lens design was taken over by Sony when Konica Minolta sold its imaging department. The focal ratio or f-number of typical mirror lenses are a bit high, which means that it's not very bright optics. Higher f-numbers means darker images compared to lower f-numbers. That means it is necessary to use higher ISO settings as well as slower shutter speed. Longer exposures during astrophotography means higher requirements on the alignment of the star tracker. Finally, I can mention that the obstruction caused by the secondary mirror also creates an unwanted variation in light intensity at the image plane. An image of a white surface will have a donut-shaped variation of intensity caused by the mirror. Astrophotographers know how to compensate for this in post-processing using flats. The secondary mirror also creates an effect where out-of-focus highlights tend to become donut-shaped light. That is not an issue for astrophotographers, but for terrestrial daytime photography that can create some problems. Some out-of-focus backgrounds can become extremely busy. Instead of the often desired creamy bokeh background, it can become a sea of donut-shaped spots. But then again, that is not an issue if you're an astrophotographer. In summary, mirror lenses in general have many advantages, but also some drawbacks. Now we can focus on the specific performance of the two Tokina lenses. First, we will have a look at one of the more important things in astrophotography, which is optical resolution. When looking at small details, which is common in astrophotography, it's important to have good optical resolution. The bottleneck is usually the aperture. The angular optical resolution is related to the diameter of the aperture as described by the Rayleigh criteria. The resolution is inversely proportional to the diameter of the aperture. Wider aperture means higher resolution. If one lens has twice the focal length compared to a second lens, it will have twice the magnification. But if both lenses have the same aperture, they will have the same optical resolution. The lens with the longer focal length will just magnify unsharp parts without adding any fine details of the image. The 400mm lens in this comparison has wider aperture than the 300mm lens, which should make more details visible when comparing images. But the optical resolution also depends on the design of the optics, which means that there is no guarantee that the advantage of the wider aperture can be efficiently used. First, let's have a look at the main specifications of the two lenses. Let's have a look at the 300mm lens. It's extremely lightweight at 298 grams. That's fantastic. I mean, this lens corresponds to a 600mm telephoto lens for a full-frame camera. So this is tiny. The length of the lens is just 55mm. And the f-number is 6.3, which is fairly good for this kind of lens. The aperture is fixed and the focusing is manual. I calculated the aperture of the optics from the f-number and the focal length, and it should be somewhere around 47.62 millimeters. If we instead look at the 400mm lens, it weighs 355 grams according to the specifications, but that doesn't include the adapter part of the lens. So I checked the weight on my scale and it's more like 439 grams. That means that it's considerably heavier than the 300mm lens. When we look at the length of the 400mm lens, including the adapter, it's about 125 millimeters. which is more than twice the length of the 300mm lens. Then we have the difference in f number. The 400mm lens has f number 8, which means that it's not very bright. Then we have the focusing, which is manual, and I calculated the aperture of the optics from the f number, and that makes it 50 millimeters compared to 47.62 millimeters for the 300mm lens. That's not much of a difference. It's just about 5% wider aperture for the 400mm lens. It took some time to do this video since it was cloudy much of the time and the viewing conditions weren't optimal, but it was okay when I shot this image of the moon. When making the comparison, I cropped the images to get the same magnification from the two lenses. That way it will be possible to see which lens has better optical performance. Let's have a look at the first image. We start with a look at the northeastern part of the moon. As you can see in the images, the 300mm lens seems to have better contrast and appears to have at least the same amount of details as the 400mm lens. We need to look at some more images before making a final judgment. The second image of the moon is the Mare Crisium on the eastern rim of the moon. In this image, the 400mm lens seems to have a bit better resolution than the 300mm lens, but still the contrast is lower, so the 300mm lens appears clearer, while the difference in resolution is surprisingly small. I was expecting the 400mm lens to be a bit better than this. The next image shows Mare Nectaris, also on the eastern side of the moon. Here the 300mm lens appears clearer and with higher contrast. It makes it easier to see details, although the 400mm lens, as expected, reveals a tiny bit more details. The lower contrast makes the 400mm lens seem more washed out. The last image of the moon shows the southeastern part of the moon. Here the 400mm lens shows more details on the craters than the 300mm lens. In general, the 400mm lens seems to produce images that feel more three-dimensional. Still, the 300mm lens is very sharp and has high contrast, which also makes it easier to focus. I only have one deep sky object to compare, which is the Orion Nebula. It is not a fair comparison since both images are not shot at the same occasion. Also, the 400mm lens shot the image as ISO 6400, while the 300mm lens image was shot at ISO 1600. That puts the 300mm lens at an advantage since higher ISO means more noise and lower dynamics in the colors and the intensity. The 300mm lens also had an exposure time of 40 seconds, while the exposure time for the 400mm lens was only 13 seconds. The 400mm lens would probably do a lot better at ISO 1600 and longer exposure time, but it's worth noting that for deep sky photography, the 300mm lens has an advantage being brighter with a lower f number. As a consequence, it gathers more light, which reduces the exposure time. The difference in resolution should be the same as for the moon details, but the 400mm lens will need more exposure time. If I have the chance to capture the nebula using the same ISO setting for both lenses, I will make this comparison again. But I think the moon images tells us what the difference is between the two lenses. So, which are the conclusions of this comparison? In my opinion, the 400mm lens has almost the same resolution as the 300mm lens, but the aperture ratio is f8, making it less bright. For some reason, the contrast is lower. I suspect there may be internal reflections causing this problem. The 400mm lens was not specifically designed for the Micro Four Thirds system. It is adapted to this standard. I can guess that it was designed for a full-frame camera. Those have lower requirements than the crop sensor cameras, since the crop sensor cameras magnify the image. So why is the 300mm lens so good in comparison? The reason is that the lens is specifically designed for the Micro Four Thirds system. It's like comparing a tailor-made suit with a suit from the department store. One lens is optimized for the Micro Four Thirds system and the other is adapted to it. I really like the old school Japanese optics, where the emphasis was on the engineering performance. In recent years, it seems Japanese companies are becoming more profit-oriented, and to design a lens that will work for all standards makes sense from an economical point of view. To prioritize performance for the biggest market, which I assume is the full-frame cameras, also makes economical sense. But from engineering perspective, I would instead think about which standard has the highest optical requirements, design the lens for that standard and then adapt it to all the other standards. My impression is that the 400mm lens is not optimized for the Micro Four Thirds system, and after looking at the daytime images, I have seen that it appears to be a bit of reflections inside the lens barrel or the adapter. My guess is that this may be the reason for the lower contrast in the images of the moon. The reflections make the images more washed out. I will make a daytime comparison later to see if the 400mm lens may be better for other types of photography such as wildlife. So in summary, I would say the 300mm lens is the better choice in almost every way. It is easier to focus, it is brighter, it is smaller and very lightweight. The 400mm lens has slightly better resolution, but it is not noticeable in the images. Unfortunately, the 300mm lens is no longer produced and can probably only be found on the second-hand market, while the 400mm lens is available. If I had to choose between the two, I would pick the 300mm lens. If Tokina had tailor-made the 400mm lens for the Micro Four Thirds cameras, I'm convinced that it would perform better. But I don't expect third-party lens makers to invest in design specifically for the Micro Four Thirds market, since Olympus sold its imaging division to JIP. The Micro Four Thirds standard was created by Olympus and Panasonic, and now Olympus has given up. We will see what happens with the Micro Four Thirds lens market. In any case, if you can find the 300mm Tokina lens for Micro Four Thirds cameras, I can recommend it. That was all for this time. If you like this video, remember to like and subscribe. You can support the channel on Patreon. See you in the next video. Have a nice day and many starry nights.